So let's go ahead and get to it. As always, we'll be recording our look through of the notes today and make sure to post it on the Google Classroom later on. Right, oh, hold on, that's the people section. Right up here in the Google Class videos section for October 8th. So today we're going to be talking about density, what it is and how we can measure it. So as always, the notes are posted down here in the week 6 units and density measurements. One announcement I wanted to make before we get started. It doesn't impact this class too much, but in case you have not already heard, there is no school on Monday. So Monday is going to be another teacher development day. And so there is no classes on Monday. So while normally we don't have class on Monday anyways, it also means that no new assignments are going to be posted on Monday either. So if you're all caught up, you have a free day. If you still got a couple assignments to do, you can use Monday to work on them if you want, but nothing will be posted on Monday. Nothing is going to be due on Monday. We won't start up back at school until Tuesday. So Monday, October 12th, no school, no class, no assignments. All right, wanted to make sure that I mentioned that before we go ahead and get started today. So our October 8th notes for this Thursday are all about density, which is something that you may be sort of kind of familiar with and have a general idea in your head about what we mean when we talk about density. But today we're going to focus on scientifically, what does density refer to? What do scientists mean when they talk about or when they measure density? So that is what is up on the docket for today. So when you think about dense things, you think about things that are like heavy, right? Things that even if they're really small, they're kind of difficult to pick up. And that would make you think, oh, that's really dense. And partially that is what we mean by density. So density is, scientifically speaking, a measurement of what's called the compactness of a material, or how compact all of the atoms, all of the molecules in a particular substance are. So how close are the atoms and molecules to each other? If you have an object that has very, very close together, compacted in atoms and molecules, that would be more dense. Or if you have an object where the atoms are a little bit more spaced out and further apart, that would be less dense. So it's different than heaviness, right? It is how much, it also relates to how much space an object takes up. So if you're picking up like a cardboard box, right? An empty cardboard box, and a little one is super light and easy to pick up, and a big one is a little bit heavier, but it's like, oh, well, it's way bigger and heavier. That doesn't mean that the heavier one is denser than the light one. They both, since they're made out of cardboard, they both have the same density. It's just that one takes up more area, and so it has more mass. It's heavier. On the flip side of that, things like weights that you pick up at the gym the heavier ones are more dense. So you go and you pick up a 20-pound weight, and you go and you pick up a 50-pound weight, and they're pretty close to each other in size, right? The 50-pound one isn't hugely bigger than the 20-pound one, but it's a lot heavier, which gives it that extra density. everything in the world has density. Liquids and solids are pretty typically thought of when you think about density, but gas also has density. Now, gases tend to be very light and not very dense, but they still do have a density that we can measure. And so a big part of today is going to be talking about how do we calculate or how do we measure density. So to illustrate kind of what we mean by compactness, again, it's relating to how much space there is between the atoms or molecules of a substance. So like this substance up here is less compact than this one down here. Our top substance has lots of atoms and molecules, but they're a little bit spaced out from one another. They're not completely overlapping. So this guy would have less density. Whereas down here, we have a very tight and compact set of atoms. They're very close together. They have a lot of overlap. So this guy is more compact and therefore more dense. So density is just a way of measuring kind of how spaced out or close together are the atoms in this substance. High density means more compact, more squished together. Low density means less compact, more spread out from each other. So the way that we can measure density is through a very simple calculation. Density is the amount of matter per unit volume, which is a fancy way of saying density is the ratio of mass to volume. So the heavier something is, the more dense that it will be. But if something takes up a lot of volume, if it takes up a lot of space, that's going to make it less dense, right? So it's this balance between how heavy something is and how much space that it takes up. If the volume of a substance or something that we're measuring stays the same, but the mass increases, so we have the same size object, but it is heavier, or we made it heavier, that would mean that the density of it increased. We increased its density. So imagine that you had like an empty like Tupperware container, right? It's pretty light on its own. There's not a whole lot of stuff in there. But if you add in a whole bunch of leftover food, like pasta or soup or something like that, the volume is still the same because your Tupperware container is still the same shape and size, but we made it a lot heavier. We added all that extra mass in there. So by doing that, we increased the density of your Tupperware, essentially. We added more mass while keeping the volume the same. On the flip side, if we keep the mass the same, but we increase the volume, we spread out the substance, then its density will decrease. So if you take, I'm trying to think of a good example for this. So it's sort of like if you have some pancake batter and you just put a big glop right onto the skillet, the hot skillet, and just let it cook there, you're going to end up with a pretty dense pancake because it's a set amount of mass, but a pretty small volume. Or after you put the exact same amount on that skillet, if you spread it around and make it really thin, now your pancake is going to be less dense because you spread out that substance. So again, density is how heavy is it compared to how big it is. If it's very heavy and it takes up a small volume, that is a very dense object. If it is not very heavy and it takes up a big volume, that is a very not dense object. It has low density. All right. Any questions about what density is or what it's referring to so far? Alrighty, doesn't sound like it. So we'll keep on moving to probably one of the most important slides that we're going to talk about today, which is the equation for measuring density. You thought that we were done with equations in chemical reactions, but oh no. Luckily, this equation is very, very simple. The density of the object, so the D, meaning density, is equal to its mass, aka its weight, divided by volume, aka how much space that it takes up. So D equals M divided by V. Density equals mass divided by volume. So this could be represented in a couple of different ways. Usually the mass is in grams. So we're talking about however many grams that something weighs. And the volume is usually represented by either cubic centimeters, so those CM3s that we were talking about on Tuesday, or it could also be liters or milliliters, so an L or an ml, depending on what exactly that you're measuring. So if you have an unknown object that you're not sure what its density is, if you can weigh it and you can measure it and get its volume, you can do the mass divided by the volume, and that will give you the density of that molecule. So just for a quick example, say that I had a wooden block, and my wooden block weighed, I don't know, it's pretty small. So it only weighs 25 grams. And it has a volume of 10 cubic centimeters. So we do the length times height times depth, and that gives us our 10 cubic centimeters. So it weighs 25 grams. Its volume is 10 cubic centimeters. So if I want to figure out the density of my wood block, I can do 25 divided by 10. And so in this hypothetical example, our wood block has a density of 2.5 grams per centimeters cubed. Because again, we did grams divided by centimeters cubed to get our measurement. So that is what our unit ends up looking like. So if you know the mass and you know the volume, you can pretty easily calculate the density of an object. So because we have this equation here, what that also means is that if we have the right information, we could also potentially calculate the mass, or we could calculate the volume of a substance. So here we have this guy, like I like to call the density triangle, the DMV triangle. And so the way this works is that if you're trying to figure out one of these measurements, but you have the other two, you can do an easy math equation and figure out that measurement. So, for example, the way that you use the triangle is that you cover up the one that you already know, and you use the remaining two to figure out your equation. So like the example that we just did earlier, we did not know the density. Sorry, I had that flipped around. You cover up the one that you're looking for and then do the correct equation with the other two. So like with our wood block example, We know the density, so we'll cover up density. And then our triangle says that in order to figure out density, we have to do mass divided by volume. And so we do our mass number divided by our volume number, and that will tell us our density. On the flip side of that, if we know the density and we know the mass, but we want to figure out the volume of our object, we cover up RV for volume. And then now our equation says that if we do mass divided by density, doing the mass number divided by our density number will tell us our volume. And then finally, if we want to know the mass, but we know the density and the volume, we can do that as well. So we know the mass, so we cross out mass. And then our triangle says that to figure out mass, we have to do density times volume. So what this is illustrating is that if we have two of these numbers, we can figure out what the third unknown is, what the third number is supposed to be. So for example, if we wanted to know the volume of a certain hunk of metal that had a mass of 50 grams, but I'll write it over here, a mass of 50 grams and a density of 5 grams per cubic centimeters. Then our volume equation says that we're supposed to do mass divided by density. So a mass of 50 divided by a density of 5 would give us a volume of 10. So since we knew the mass and we knew the density, we were able to calculate our volume. So I'll do one more simple example. If we know the density and we know the volume, then we can calculate the mass. So say we have an object that has a density of 3 grams per cubic centimeter, and it has a volume of 7 cubic centimeters. Then our mass equation says that we need to do density times volume. So 3 for our density times 7 for our volume gives us 21 grams for the mass. All right, so while the density equation is d equals m over v, mass over volume, hopefully by doing these examples, you can also see that as long as we have any two of these three, then we can figure out the one that's missing. So if we have two numbers, we can figure out the third one using one of these equations where you just plug in the two numbers that you already know to figure out the third number that you're looking for. All right. This is the main thing that your homework is going to be based around for today and tomorrow. So now is the time to ask questions if you're still not 100% sure how this works.
So the ending of them, how you just had 21 grams, you didn't have the CM3 or whatever. Does that play a big part?
Not really. Essentially, I was just trying to save time by not having to write out all the different little units. So those are just the units. That's just telling you, is this something that's measured in grams if it's the weight, or is this measured in cm3 if it's the volume? And so if I wrote it again, boy, that was this one. So it would be, if I wrote out the whole thing, it would just look like, what was it? 3 grams per centimeter cubed times 7 centimeters cubed equals 21 grams. So I know it's grams because we're trying to find the mass, and the mass part of the density equation over here was in grams. So I know that grams is going to be part of our final answer.
Okay.
Good question. So when you're doing the equations, you don't necessarily have to write out all of the units, but your final answer should have a unit on it. So if I ask for the density of something, you can't just tell me that it's 2.5, right? 2.5 is not a density. That's just a number. But 2.5 grams per, say, milliliter, that is a density. So just make sure on your final answers on the homework and the worksheet that you include the units. Good question. All right, so I'll show you what the homework for tonight and tomorrow look like in just a second. But first, I want to talk about a couple different things that can influence the density of an object, or a couple different interesting ways that density works. So one thing that sometimes trips people up is the idea of gases having density, right? Gas is like an invisible, weightless thing that's all around us. How can gas be more dense or less dense? Well, gas is not weightless. It does have weight to it. Now, in general, it's an extremely small weight, but gas still has weight. So gas has density. So if you remember way back when we were talking about solids, liquids, and gases, I mentioned that kinetic energy is a measurement of how fast that the particles are moving around. So in general, when particles are moving around very fast, when there is a high kinetic energy, it causes the particles to expand further apart from each other. So we increase the volume when our particles are moving. And like we mentioned, if our volume gets bigger, that means that our substance gets less dense. So cold air, where the particles are moving slower, is more dense than warm air, because as the particles move faster, they get further apart from one another, meaning bigger volume. And when we have bigger volume, we get less density. So if you've ever seen hot air balloons before, this is the exact premise that hot air balloons are based on. So you've seen them floating through the air, and you've seen the person open up the little vent and fire kind of shoots up to the inside of the balloon. The fire is heating up the air inside of the balloon. And since the hot air in the balloon is less dense than the cold air, let's see, hot air density is less than cold. That cold air density. So because the hot air is less dense, it rises above the cold air. And when you have a lot of hot air, you're able to pull heavy things like a balloon basket and people above that cooler air. So the cooler that air gets, the lower it will fall. That's why in like the summertime, if you have a 2-story house or a 2-story apartment and you go upstairs, it in general will feel a little bit warmer than downstairs because the hot air rises up to the upper area of your house and the cold air will fall down to the lower area. So that is a way that gases interact with each other when it comes to their densities. Liquids can also have different densities. So like in this cup, this beaker over here, we have 3 different liquids, but their densities are very different from one another. So the most dense liquid, this, I think it's like oil down here, like motor oil, sits on the bottom. Above that is a clear liquid, could be something like water, that has a medium density. And then something with a low density, which in this case looks like some sort of like cooking oil or something like that, sits on the top. So liquids also differ in density, not just the type of liquid, but also the temperature of the liquid can also affect its density. So cold water is more dense than warm water. Just like how we talked about in air, cold is more dense than hot. Same thing in liquids like water. So in lakes, cold water tends to sink down towards the bottom, whereas the warm water will sit more on top. And so this especially happens in lakes far in the north during the winter time, when it's like in Michigan or Minnesota or something, and the air gets super duper cold. The top of the lake actually starts to get colder than the bottom of the lake. So the water at the top of the lake will sink down to the bottom and cause this big upwelling of water to the top. It doesn't happen in like one big spread, but it's really important for keeping the waters of the lake mixed throughout the course of the year. We can also have differences in liquid density depending on if we have a whole bunch of stuff dissolved in our liquids. So like, for example, ocean water that has a lot of salt dissolved in it is more dense than fresh water. You may have noticed if you ever gone swimming in the ocean, it's easier to float on the water in the ocean because it's more dense. And so it's easier for humans to kind of stay on the top. This is especially true for extremely high salty areas. So the Dead Sea in the Middle East is a good example of this. It is a lake that has an extremely high concentration of salt in the lake water. So people can literally like bob up and down on the top of the water with almost no effort because the water is so dense due to all of those dissolved salts in them. So imagine that we have a substance like mercury, which is normally a liquid at room temperature. It's one of the few metals that's a liquid at room temperature. It looks really cool. It's like this little quicksilver effect. Say we had a big vat of mercury. The mercury is a pretty dense material, 13,600 kilograms per meter cubed. Dense stuff. And then say we had something made out of lead, like a big ball or something, that is a little bit less dense. The lead is 11,340 kilograms. And we plopped it into our mercury. So our mercury is liquid, our lead is solid. We dropped like a lead rock or a lead brick or a lead ball into the mercury. Normally, you'd think that, oh, the solid will fall to the bottom of the liquid, right? If you throw a rock into the lake, it sinks down to the bottom. But notice their densities. Mercury is more dense than lead. So what ends up happening? Lead floats on liquid mercury. So this is a picture of a old school pool ball when they used to be made a lot out of lead. And here we have a glass full of liquid mercury. So this ball is floating on the top of this liquid metal because the lead is less dense, the mercury is more dense. So things that are less dense will float or go to the top of things that are more dense. So solids in general are the most dense type of matter. Their densities can be all over the place. So rocks versus metal versus woods versus certain elements all have different densities that are based on what sort of substances are in them. So like gold, for example, is a very dense substance. These bars of gold aren't that big. I would guess one would be about, I don't know, this long or so, but you hold one in your hand and it's really heavy. So a lot of metals are very dense, whereas a lot of different types of wood are fairly non-dense, right? You pick up a big stick and it's not too difficult to hold on to. So one really cool exception to the rule is ice. Solid water, aka ice, is actually less dense than liquid water. So that's why we have icebergs that float on the top of the ocean. That's why the ice cubes that you put in your drink float on the top. You don't drop an ice cube in and it just sinks down to the bottom, right? It has to do with the particular way that the H2O molecules line up and freeze in place when they become solids. But this is a really important thing that helps life on Earth survive because it means that things that live in like ponds and lakes that freeze over in the wintertime are able to survive underneath the frozen water because all the ice is sitting up here at the top. If ice was like a normal solid where it got more dense when it froze, you'd end up with these big sheets of ice freezing on the top of the lake and then dropping down and crushing everything below. So while usually the liquid form of an atom will be less dense than the solid form, ice is a really cool exception. Other things that can affect density are temperature. So we already mentioned that hot air will rise above cold air and cold water will fall to the bottom of the lake and be under the warm water. Pressure can also affect density. So if you put certain substances into a high pressure or low pressure areas, the density of them can also change. And then, like I mentioned earlier about ocean water with its salt, the types of substances and how concentrated those are dissolved in the liquid can also contribute to the density of a substance. So in general, the more concentrated your dissolved solid is, the more dense that your liquid will become, right? So if you put a little bit of salt into a pot of water, the water will become a little bit less dense. But if you take a cupful of water from the Red Sea that has all of that high salt content in it, you end up with a relatively much more dense glass of water. So then finally, we have our density table over here. So this shows a whole bunch of different densities of different substances from wood to aluminum to gold to ethanol or ethyl alcohol. And we're going to compare that to the density of water. So water is really neat because pure water has a density of 1.0, 1 gram per cubic centimeter per cm3. So totally pure water is exactly 1.0 density. And so we can compare these other substances to water and see if we drop this substance into water, would it sink or would it float? Is it going to be less dense than water that cause it to float up on the top? Or is it going to be more dense than water and drop down to the bottom? So obviously air is extremely low density, right? Gases tend to have very low density overall. So air will obviously float in water. If you put some air bubbles into your water, or like the carbon dioxide bubbles in a soda, they're always going to want to come up to the top because they're very, very low density. Same thing with wood. So that's why a lot of times if you throw like a log into a lake, or even things like sticks and twigs will generally float on top of the water. Ice, like we mentioned before, is one of the rare solids that will float on water. So ice has a density that's just a little bit under water. So if we have our totally pure water at 1.00 grams per centimeter cubed, when we freeze that water, it becomes a teeny bit less dense, 0.93 grams per centimeters cubed. So aluminum is our first example of a substance that'll sink in water, right? You take a big wad of aluminum foil and toss it into a lake, it's going to drop to the bottom. So aluminum 2.7 grams per centimeter cubed, so a little bit more dense than water. Lead is very dense metal. It has a density of 11.3, obviously much higher than water, so lead is going to sink straight down. Gold, even more dense than lead. Like I was talking about earlier, should you ever have the privilege to hold a gold bar in your hand for some reason, it's going to be a very hefty piece of metal. Our alcohols, on the other hand, things like ethanol, which is the type of alcohol that is present in most of the things that we drink, or methanol, which is a version of alcohol that can be used as fuel for certain types of engines. These guys both have a fairly low density. So ethanol is a little bit less dense than water with at 0.94. Methanol is much less dense than water at 0.79. So because our drinking alcohol, our ethanol, is a little bit less dense than water, that's why if you've ever been at some bars where they have a specialty shot that they light on fire, they're able to do that because they'll pour a little bit of an extremely high alcohol drink like Everclear or Bacardi 151 or something on the top of the drink or the shot. And so the alcohol stays up on the top, and that's why you're able to light it on fire, because also ethanol, very flammable. So density is a measurement of compactness. We measure it based on how much an object weighs compared to how much space that it takes up. Density can be affected by a whole bunch of different factors, but whatever they are, the final density tells us about how compact an object is. So things like ice and wood, and especially air, are relatively not very compact, whereas aluminum and lead and gold are very, very, very compact material. You can get a lot of mass into a fairly small area with these heavy metals. All right. Any final questions about what density is, how to measure it, or what it means?
I'm good for the most part.
Awesome. Thanks, Stacy. So to give you a quick little kind of overview of what you're going to need to know for the assignments coming up from today and tomorrow, they're mostly based around making these simple density calculations. So our first one that got posted earlier today has a couple of different questions, and it asks you to calculate a certain measurement, either density, mass, or volume. So if you need a reminder of what the density equation looks like, it's written up here in our first example question. So like for questions 1 or 2, it gives you the mass and the volume of certain material and asks you to calculate the density. So density is mass divided by volume. And so that's what you'll do for the first 2 questions, mass divided by volume, to figure out density. For the next couple, it switches it around a little bit. It gives you the density and it gives you the volume. And for number 3, it asks, what is the mass? And then number 4 changes it up a little bit. It gives you the mass and it gives you the density, and it asks you to calculate the volume. Then finally, for number 5 and number 6, they kind of go together. You have to do a teeny bit more calculations than before. It gives you the mass and it gives you the dimensions of a rectangular block. And so the first thing that you have to do is you have to calculate the volume. So it doesn't just give you the volume, you have to calculate it. So you do the classic width times height times length measurement. And then based on the answer for the volume that you get, you now have the volume and you have the mass. So you should be able to calculate the density based on our density equation. Then the worksheet that's going to be posted tomorrow is pretty similar. It asks basically the same types of questions using the density equation, solve a couple different problems. So if it gives you a volume and a mass, you know that you have to calculate the density. If it gives you the mass and the density, that means that it's going to ask you to calculate the volume. Or if it gives you the density and the volume, you'll have to calculate the mass. And finally, number 5 changes it up ever so slightly. It tells you the density of 2 different substances, silver and aluminum. And it then gives you the measurements and the mass of a unknown silver colored metal. So silver and aluminum are both silver colored, right? If I just handed you a piece of metal and said, is this silver or is this aluminum? You probably would have a tricky time telling just by looking at it. So first you have to calculate the volume. Then you have to use the volume and the mass to calculate density. And based on the density that you calculate, you have to tell me, is the unknown metal the element silver or is it the element aluminum? And that is all the work that you have to get you through the rest of this week. Again, that first assignment got posted earlier today, and the second assignment will be posted early tomorrow morning. So, any final questions on density density calculations or what you have to do for your assignments this week.